Okay. Great. Welcome, everybody. Welcome. This is the Combating COVID-19 with AI workshop. We have a special guest from Darwin AI, which is Alex Wong. He'll be giving a presentation. I will then talk about Rmnn and how ARM fits into this, and then Wei will begin conducting the workshop where you'll get to test all the things we're about to talk about. Quick housekeeping slide. That's today. If you're experiencing any audio issues with the device, you can use your phone to call in. The call-in numbers have been added to the chat. Today's presentation is being recorded and will be available within 24 hours on the ARM DevSummit site. So just in case you want to go through this workshop stuff later and want to watch the video, that'll be available. You can also share it with people because, hey, the more the merrier. We welcome your comments and questions for the speakers, but we are going to have a dedicated Q&A time at the end. So just keep that in mind, just because we do want to make sure we finish and leave room in case people get stuck. Type your questions into the chat box at any time during the workshop, and make sure you send it to everyone and not just the host, because if it's just the host, not everyone will see it. If you have any questions about our code of conduct, please see the facts. If for some reason the Zoom meeting ends prematurely, please try the link again from the ARM DevSummit site right away. And if that doesn't work, wait 10 minutes and then try again. Okay. With that being said, I'd like to introduce Alex Wong from Darwin AI, and he's going to talk about their platform, their product, and how what the work they did related to COVID. And I will end this and stop sharing. And take it away, Alex. Thank you so much for coming, by the way.
Let me know whenever you see my screen.
I can see it now.
Perfect. So thank you very much for, I guess, the opportunity to talk during this summit. It's been exciting so far. So hopefully you'll enjoy what we have to show for you here. So here I'm just going to talk really briefly about our COVID-Net initiative, which was launched between, I guess, Darwin AI as well as the University of Waterloo. So I'm Alex, Canada Research Chair in Artificial Intelligence and Medical Imaging, as well as a professor at the University of Waterloo. So let me talk a bit about this particular endeavor that we've went into and how it came about. So here's just a quick, I guess, overview of the COVID-19 pandemic, which most of us don't need any more introduction given all the news flowing around. But one of the things I would like to highlight is even just looking at this Johns Hopkins COVID-19 dashboard, this was actually not captured too long ago, but the number of global deaths have already hit 1 million, as well as the total confirmed cases is 35 million. And so you can see that this is a pandemic of pretty much global proportions that we're all struggling to try to deal with. And so one of the key main steps to the management of COVID-19 around the world has been screening, which is the very first step in the clinical workflow. And so the standard approach that's often used is what we call RT-PCR testing. So that's, you've seen like the nose swabs or the throat swabs, that's what it is. So it is the gold standard. It has very high specificity. So when it says somebody has COVID, chances are they really have COVID. But there are a number of issues with this approach. One is that it's a very time-consuming process. So right now, after all this time, it still takes a day or more. But before, we had cases of up to 7 days, all the way to over a week just to get results back. So with a patient that has respiratory complaint as well as symptoms, what do you do with them in the meantime while you're waiting for RT-PCR test results? It's also a very lab-intensive process and is still in short supply in many countries. One of the more alarming things recently has been the variability in terms of the sensitivity. So depending on where you swab, whether it's your throat or your nasal passage, that can change sensitivity. But the more troubling part is in a recent study, what they found is that the positive rate goes down as symptom onset. So the longer somebody has COVID-19, the less likely it will be detected using RT-PCR tests. So more recently, to speed up the process, people have looked into antigen or antibody testing. And so those give really fast results, usually on the order of minutes, as you've seen in a lot of systems nowadays. And it also has very high specificity. But the biggest problem here is, you can see on the right, the sensitivity to COVID-19 is actually quite poor. And in fact, in one of the more recent studies from the National COVID Scientific Advisory Panel in the UK, they found that currently available commercial commercial devices do not perform sufficiently well for individual patient applications. And so that has kind of put a little snag into its widespread adoption. So where can we go from there? That's where the approach of chest radiography really comes into play around the world. So doctors, clinicians around the world has been leveraging chest radiography as a complementary screening approach. And in some cases of short supply of viral tests, it's actually been leveraged as the primary approach. And there's a number of reasons for that. One of the first reasons is just rapid triaging. It's a very fast process, a very fast acquisition, can be done in parallel to viral testing so that while you're waiting for viral test results, you can actually figure out how to actually help a patient at that particular time, because we're talking about really, really quick interpretation times. And often the other key thing is that it's often already used as a routine procedure for patients with respiratory complaints. So because we're doing it anyways, why not leverage it for COVID-19 detection as well? The other key thing is accessibility as well as availability. So in general, chest x-rays or chest radiography is actually low cost, low maintenance. And the other key thing is that it's readily available in most clinical sites around the world. In fact, as we know, chest x-rays is standard equipment in almost all healthcare systems, even in developing countries. The other key thing about chest radiography that's an advantage is that it's a very the existence of portable systems. So there are very portable systems that can be performed in isolation rooms to minimize risk of transmission. It can actually be brought to rural areas. We've actually seen cases where people have flew portable chest x-ray systems directly to remote areas where there's no healthcare providers available. And it's also very easy to contaminate as a standalone unit. But most of all, the most important thing that you get from chest radiography is the notion of risk stratification. So while viral tests like RT-PCR tests and so on and so forth allows you to kind of determine whether somebody has COVID-19 or not, or the likelihood they have, it does not give you any indicators as to the risk level or severity of the actual impression. So you really don't know about disease progression. And so with chest radiography, you can actually get a very good sense in terms of risk level and severity. And that information can be used to improve population management, individualized care based on risk, as well as resource allocation. So because from talking to clinicians around the world, what we were doing, we were very motivated to create an initiative to help them in their particular clinical decision support. And so that's where we introduced COVIDNet, which is a global deep learning initiative for COVID-19 detection and risk stratification from chest radiography. One of the key unique aspects of our initiative is that it's completely open source and open access, so anyone can build upon it. Anyone can customize it for their own deployments as well as their clinical needs. And that's a link to where you can find it. And the other key thing is that because of its widespread use, we continually improve it and we do regular updates of new models and data. And that will lead to some of the things I'll talk about in terms of rapid development of deep learning to facilitate for regular releases of new and updated models. It started as a team of two, myself and Linda Wang, which is my student, but now it's grown to a larger international team. And now we're quite happy that COVIDNet is used around the world in all continents, as well as receive great global support, as well as media coverage. Special thanks to ARM for the support in our initiative. So it started off as a joint initiative between the Vision and Image Processing Research Group that I run at the University of Waterloo, as well as DarwinAI, which is a company that I helped co-found it, where the mission is to solve operational challenges in AI and machine learning to enable widespread adoption of AI across verticals in a scalable and trustworthy manner. And so now I'm just going to get into some of the technical aspects of the initiative. So first of all, the COVIDNet initiative is composed of three main initiatives. One is the COVIDX initiative, which is to create the world's largest open access benchmark dataset for chest radiography for COVID-19. Next is COVIDNet CXR, which is where we design tailored deep learning models for SARS-CoV-2 detection from chest radiography data. And finally, we have COVIDNet S, which is building tailored deep learning models for SARS-CoV-2 severity assessment from chest radiography. And so you take a look at the right, you start off with a chest x-ray or a CT scan. It goes into COVIDNet, which then will determine whether somebody has likelihood of having no COVID infection, having a non-COVID infection or a COVID-19 infection. And in the case where they have very high likelihood of having a COVID-19 infection, it goes into COVID-NET-S, which will then produce severity scores to help clinicians better determine the patient's progression, their conditions, to better treat them. So one of the key things that we were faced with was, how do we actually build this fast? We needed to build COVIDNet at a much more accelerated pace, given the urgency of the pandemic itself. And we wanted set our goal to having it built in less than 7 days to act as a reference point for the global community to build upon and drive innovation. So the problem we have at hand from a technical perspective is we need to build custom tailored deep learning solutions for specific tasks and specific requirements that usually takes months to a year, even for large enterprises. So how can a small team of 2 at the time, build deep neural networks tailored for COVID-19 detection and risk stratification in a much shorter time frame, especially getting a point that meets our operational requirements, especially for deployment in chest radiography systems? And so the idea or solution that we came with was we combine human expertise and experience through human-driven design guidance with machine-driven design exploration and understanding to enable a human-machine collaborative design approach. And there's a number of different advantages to this approach. So first of all, the first benefit is that it provides accelerated scalable development beyond what humans and AI can do independently at a much faster rate. More importantly, it gives much greater transparency into the model design and performance for more trustworthy deep learning development and regulatory compliance, which is very important from a healthcare perspective. And it's also very important to help developers figure out what are the quirks, gaps, and nuances that needs to be resolved. And so the whole idea of human-machine design collaboration is based on the notion of explainable design automation, which is a radical idea that we came upon, which involves working with an explainable AI, in this case through the DarwinAI Gensive platform, to design highly efficient, highly accurate, highly dependable deep neural networks based on human-driven design and requirements. And so here we treat AI as a collaborator. So an explainable AI learns from operational requirements, including the need to have it running on embedded processors such as ARM processors, and prototypes and explain to a generator, which will automatically generate different designs, different solutions with different trade-offs. And so a developer can then iterate with the AI agent to rapidly build customized solutions tailored for the task at hand. And so this allows us to develop unique machine design networks tailored around human requirements and the task at hand, as well as the discover insights through this machine-driven design exploration process can then be surfaced for greater transparency and trust for both the developer as well as the end user. And so there are 4 key steps to this particular human-machine design collaboration approach, which I'll go through in the context of building COVIDNet in less than 7 days. So first thing is data collection. And so if we were able to manage to collect COVIDX, which is the largest open access data set of its kind, with over 14,000 chest X-ray images collected across 4 continents under different views, so anterior, posterior, posterior, anterior, using different equipment, so both portable as well as fixed systems, as well as under different protocols and different positions, including supine, upright, so on and so forth. And having this large data set from across the world allows us to have much better diversity in terms of data, which leads to better generalization when building your deep neural networks. The next step that is a bit different than the usual deep learning development process is what we call design prototyping. Rather than iterating manually through to figure out what's the best architecture for my particular task, what we do here is build a MVP minimum design prototype, which might not even have to be trained properly. And it then acts as the scaffolding for the machine-driven design exploration to actually learn from to build better neural networks based on your task data as well as your operation requirements at hand. So in this particular case, for COVIDNet, what we did was create a very rudimentary design prototype, which is based on a simple residual architecture, as 3-class softmax output, so normal, non-COVID-19 infection, as well as COVID-19 infection. And then we leave the final macro architecture and microarchitecture design completely to the machine-driven design exploration approach in Jensen platform to then figure out what is the best neural network based on all these requirements and the scaffolding at hand. Next, we go into a design exploration stage where we take this very coarse, very rough design prototype, which we're able to put together in an order of hours, and take the data we have at hand, which is COVID-X, as well as the operational requirements based on clinical feedback we receive. So talking to clinicians, what they want is a operational requirement of at least 80% sensitivity, as well as 80% PPV. So it has a very good chance of detecting COVID-19. And when it does, in fact, detect it, it's likely to be right. So taking all of this information, we pass it into the DarwinAI Jensen platform, which goes through what we call a generous synthesis process to then automate the design exploration process to enable machine-driven design exploration. And so learning from all the information that we provided, it was able to automatically create this particular network, COVIDNet architecture, which has some very interesting characteristics. So first of all, what you see is that it has a very interesting but efficient macro architecture design comprised largely of pointwise as well as depthwise convolutions, which are very efficient. And so this makes it very ideal for running on embedded processors such as ARM processors for real-time feedback as well as screening. It has very interesting selective long-range connectivity, which has rarely been done by hand. And this allows for a very efficient propagation of information throughout the network for better training and better performance. So what you see here is that by taking this kind of design exploration approach, we're able to create hands-free creation of unique tailored designs with different trade-offs. And in this particular case, with the final COVIDNet architecture created using this machine-driven design exploration approach, it is half the complexity of a ResNet 50, but actually has 8% greater sensitivity. So not only is it a lot more efficient, it's also a lot more accurate in terms of what it needs to do. And looking at these numbers, we are able to achieve state-of-the-art performance, both in terms of performance, as well as in terms of efficiency, as well as low complexity. So this leads to architecture designs that are significantly smaller and faster for deployment on embedded processors, as well as other types of low-end processors for the edge. It provides significantly higher accuracy, as well as significantly higher COVID-19 sensitivity and positive predictive value. So usually people stop there. They're like, okay, numbers are great. I'm ready to deploy. However, the question here is, do numbers really tell all? And the answer is no. A lot of times we're ready to deploy and we don't go into additional auditing. So what we've done is we introduce a new step called design auditing, which audits the model design that actually helps accelerate development. A lot of people ask me is, how do you accelerate development by adding an additional step? It sounds counterintuitive. But with this approach, we're able to much more rapidly identify error scenarios, understand the reliability of a created model, and gain valuable insights on how to improve the model so that we can actually catch any issues or errors and mistakes very early on so that we don't get bogged down at the end by it. So this way, we're actually greatly accelerating development by making sure we don't make a lot of errors along the way. And so what you see on the right is your typical confusion matrix. But for us, with the design auditing, confusion matrix is just the starting point. So here's how we actually audit a neural network, in this case, COVIDNet, to make sure that it is dependable and trustworthy for actual use. So first step we take is what we call example-driven explainability through the DarwinAI Jensen platform. So here, it allows us to gain insights into commonalities and trends in chest X-ray images that share the same design decision scenario. So in this case, it's automatically able to retrieve all the situations where it predicts it is pneumonia, and it actually, in fact, is pneumonia. So we can actually then look for any kind of anomalies or similarities in how they make decisions. So that's our very first step. Once we show our example-driven explainability, next is we use the same kind of thing and we look into the attention, attribution, driven explainability to allow us to get insights into critical factors to the model decision. So leveraging a GenSim platform, we're able to see that in this case, here are all the cases that are correctly determined as COVID-19 infections. What you see highlighted are all the different areas where it leverages to make the decision. And this is done in a quantitative way so that it's by looking at these particular critical factors that it actually is completely influencing a decision. So in this particular case, if you look at highlighted, it's able to identify all the ground glass opacities as well as bilateral abnormalities that are characteristic for COVID-19. And this gives the developer a good sense of validation as well as certification, but also gives the user, such as the radiologist, a stronger sense of trust because they can see that what the model is using aligns very well to clinical practice. And so next, after the attention attribution driven explainability, we leverage what we call a counterfactual driven explainability approach to give us quantitative insights into the impact of the critical factors against alternative decisions. So we are saying here that the model is leveraging the ground glass opacities as well as bilateral abnormalities to make its decisions. Well, what if it's not using it? What are the alternative scenarios? So what you can see here is in the alternative scenario where it is actually not leveraging what you see highlighted, instead of being confident that it is COVID-19, it actually thinks it is non-COVID-19 pneumonia, which helps further reinforce that whatever it's been looking at, which is the ground glass opacities and bilateral abnormalities, is in fact what is relying on for detecting COVID-19. And so why is this important? Shouldn't it always make this right decision for the right reason when we get high accuracy? The answer is no. And here are two very clear cases of our early prototypes for COVIDNet where it completely fails, even though it had very high accuracy. So on the left is a very high accurate prototype that we had early on that we completely threw out the door because what it was doing was it was making COVID-19 decisions by looking at embedded text instead of looking at the lungs. And on the right is for a CT case where this one is even more ridiculous. It's getting almost perfect 100% sensitivity and PPV by looking at everything but the lung. What you see here highlighted with our explainability through GenSim is that it's actually relying on the patient bed that the patient is lying on for the CT scanner to make all COVID-19 decisions, which is completely ridiculous, makes no sense, and gives you insights into the erroneous cues it leverages that clearly shows that it might get high accuracy, but is completely useless and undeployable. And that's the beauty of doing this explainability-driven design auditing step. And so riding on the success of this approach, we've now released COVIDNet S, which is a neural set of neural networks for risk stratification, for assessing lung severity, as well as lung disease progression of SARS-CoV-2 positive patients. It's based on a clinical score, so it's able to predict exact clinical scores in collaboration with Stony Brook School of Medicine in New York State. And so we're quite happy about this. Again, we went through this 4-stage process, human-machine design approach, to automatically generate here the COVIDNet S architecture. And we were able to get a good predictive performance based on that. And right now, with the success of the different COVIDNet models we built, we are now building COVIDNet UI, which is also available right now, open source, open access, that allows radiologists, clinicians to play around and test it in an environment that will automatically use the AI that we've created without having the clinicians to have to install TensorFlow or other types of deep learning platforms. So now they can actually use the networks we built directly. And so what's next? So we're continuing to release new and improved models and data using this rapid design process through the GenSim platform. We're working with clinical institutes around the world for feedback and evaluation. We're creating COVIDNet Cloud so people have much greater access around it, as well as being able to deploy it on ARM processors on the actual devices itself, as well as incorporating additional patient metadata, such as comorbidity, vital signs, blood tests, and so on and so forth. And as a bit of marketing, we're always looking for collaborators to join the open source, open access COVIDNet initiative. And so now I'm going to turn it back to you as soon as I stop sharing.
Perfect. Thank you so much, Alex. That leads into our next section of this workshop, which is, so you've trained a model, you're trying to get something done, and now let's say you want to deploy it. And how are you going to do that? It's going to depend on what hardware you're using. And if you're running ARM hardware, let me know when you can see my screen. And it's presenting. Is that good? Cool. If you're using ARM hardware, you should be using Rmnn, basically. So I'm going to give a brief presentation over Rmnn. What is it? Why do you care? How do you use it? And then we'll move into PyRmnn, and then we'll get to Way, and that will be the hands-on portion of this section where you're taking both of these presentations and putting them into practice. This is going to be a condensed version of a talk on Rmnn and PyRmnn that was done a few weeks ago during our virtual tech talks by one of the software engineers for Rmnn, James Conroy. If you want to see a longer version of this, feel free to check that out. It's already on YouTube. And he goes into a little bit more detail where I'm just going to kind of skim over it. Okay, now Rmnn overview. What is Rmnn? So Rmnn is effectively, ooh, I have too many things. Okay, sorry, too many chat boxes open. I'm trying to watch everybody. Okay, so Rmnn is an ML inference API for Linux written in C++ 14. It is an API to access many different Rmnn and many different NN accelerated devices, effectively any kind of ARM IP that you can run on. It's broken up into several portions, which I'll go into more detail late in a minute. It's developed as open source, and right now it's running under the MIT license. That will probably change in the future because we're looking at moving over to Apache. There's the Android NN HAL driver provides access to Rmnn for Android applications. So if you're an Android developer and you want to be making sure you're running like optimal inference on an Android device, make sure you can already just use Android NN because it's built in. Rmnn also provides backends for the lower level libraries and hardware drivers. This consists of things like third-party partners, can add their own backends, and then backends can be dynamically loaded during runtime. Rmnn is also built on top of the ARM compute library, which is used to be the direct interface between the ARM CPU or the ARM GPU, that being the Mali GPU. Rmnn is also, we're already building in Ethos N drivers for upcoming NPUs, so Rmnn is already going to be supporting those by the time they come to physical hardware. Rmnn is open source, like I said, so it's meant to be contributed to, it's meant to be used. Right now it's under an MIT license. Open source is starting as a quarterly release. ARM compute library, which is kind of the underlying hardware accelerator, it's on the same kind of cadence as the compute library on GitHub. And both of those software stacks are accepted into the Linaro as part of the official artificial intelligence initiative. So if you want to get more involved, Linaro is going to be a great way to get connected to it, which is a full community of open source development. The core Rmnn components are going to be these things. Effectively, what you need is the core, which is going to be the interpreter, the parsers, which take in whatever kind of model you are going to be importing, and then things like the Android NN API if you're running Android, or ACL if you're running on top of that. This is kind of a blown up view of this slide. So effectively what you do, let's see, the colors are weird. Everything in yellow on this is part of Rmnn. So that includes the optimizer and the runtime, and what you need to bring to Rmnn is going to be the model files or the Android NN libraries that you'll be using. The models supported are going to be either TensorFlow, TensorFlow Lite, Caffe, or Onyx. If you run in PyTorch, you're going to want to take it over to Onyx first before you run it over to Rmnn. And then there's also the options for custom libraries for it. So if you're running a different backend, or our partners have a different kind of software driver for their hardware, they're going to build a custom backend, and that's documented online, and you can always build your own. Workflows so how to use Rmnn. Describe a network and optimizing it. This is definitely documented online, and I would check it out. Using the iNetwork interface, construct layers, call the network optimizer to allow Rmnn to apply a known set of static optimizations for the network. Load the network and execute the inference. Create an Rmnn Ai runtime interface. So once you've created and optimized the model, you now run it in terms of interpreter mode, in terms of the interface. You load the optimized network, you construct input and output testers, and then you run the inference, and then you're going to get the results back. The parsers supported are going to be the way to integrate with most machine learning frameworks that exist now. There's the TensorFlow Lite parser. This is an example of using that, by the way. The created network can now be optimized and inference is executed. There's a test tool, execute network, that loads and executes models so you can understand the results before you're putting it into production. If you're running, it didn't move. If you're running Android NN, it's an API integration. There's an Rmnn driver for it. Once the driver is loaded, requests will be translated through the Rmnn interface and execute the code optimized for RMIP. And in user code, you must make sure the NN API is enabled. So for TensorFlow Lite, there's a flag. Different backends. So the backends are going to be an abstraction that maps the layers of the network to graph two specific kinds of hardware. So different kinds of hardware can support one, more, or multiple layers from the graph. You can create backend specific workloads, and you can execute these workloads as you create them. And Rmnn also does allow statically linked or dynamically loaded backends. So both of these are options. Custom backends, I won't go into full detail on, but these are an option. So if you're running on custom hardware, you can build a custom backend for it. So you're going to need to know a lot about the hardware you're trying to accelerate for, but it allows it. All backends must be uniquely identified by a backend ID. Each backend can have backend optimization, and you also need to handle memory management when you're working on that. All the documents are on GitHub. Feel free to check that out after. This leads us to PyRmnn. PyRmnn is a Python extension for the Rmnn SDK. This has been worked on for a while, and now it's available for use. The interface is similar to the Rmnn C API, sorry, and it's built around the public headers. So this is just a Python wrapper for the Rmnn library. So if you're more comfortable in Python, that's why we developed this. Personally, I'm way more comfortable in Python, and I'm very happy we get to use this. All operators are delegated to the Rmnn library, and it uses SWIG to generate the Rmnn Python shadow cases in the C wrapper. More information on PyRmnn can be found on our GitHub repository, as well as more examples in terms of how can you use it in production. We are also working in terms of a new release coming out at the end of November in terms of more usability, greater ease of installation, as well as more documentation and good solution. So make sure you check out the GitHub. We'll make an announcement when that happens, and we'll probably have a few blogs, but there will be more workshops involving PyRmnn at that point. With that, it's now time for the hands-on session. Wei is going to take over from me. If you can, log into Jupyter Hub at this IP address, 3.81.206.28:8000. The username is going to be your first name. The password is Rmnn. And while everybody gets logged in, feel free to open the README PDF, which should be the first thing you see when you open up the Jupyter Lab interface. And if you run into issues or can't connect for some reason, send me a private message or chat it in the box. And I'm going to end this. I'm also going to copy and paste this to the chat box. Okay, and let's see. Everyone, let us know when you're in and logged in. And I will stop sharing my screen so that Wei can do that if I can find. There it is. If I can find out how.
Cool, thank you, Kyle. So last year, AWS rolled out a Graviton processor. This is based on 64-bit ARM Neoverse core. So because of the AWS Graviton processor powered EC2 instance, we're able to run today's workshop virtually without a real hardware device. So we already have Pyrmn and all the dependency installed on this Graviton instance. While you are logging, we will be able to walk through the hands-on portion. Cool. So once you go to the URL Kyle just shared with you, you will be able to log in by using your first name and password. Rmnn. I think most of you will be able to see this, a README file and COVID-19 directory. If anybody has any questions, please feel free to unmute yourself or just raise your question in the chat window.
Yeah, I should also add the username is all lowercase. So
True,
no
yeah, please use a lowercase.
And the password is all lowercase.
Mm-hmm. So yeah, if you open the README file, this is basically the hands-on instruction for today's workshop. I will spend a couple of minutes to walk you through the structure. So if you click on the COVID-19 directory, this is what you will see. So under Assets folder, you will see a bunch of images. These are the patient's X-ray image, lung X-ray image. We're going to use one of these images for image classification with Pyrmn. So if you go back one level, this accelerating COVID-19 inference with Rmnn PDF is actually the same as README file. So COVID-19.TensorFlow Lite. This one is the TensorFlow Lite model generated from COVID-19. So thanks to Darwin Ai, who made this possible, we're able to create a TensorFlow Lite open source model out of the work they had done. Data.py, this is a Python script. Some of the image pre-processing part is included in this script. So in our Pyrmn code, we're going to invoke some of the functions from this script. So moving down a little bit, you see two Jupyter notebooks. One is called Inference Rmnn Final. So this is the complete Pyrmn code. The other one is Inference Rmnn. If we open this, some of the Pyrmn parameters are missing in this file. So the goal of this workshop is you will be able to follow the README file and plug in some of the missing parameters. And you will be able to run image classification on the images we provided. So in case you run into any questions, you can always refer to the final version of the code. Now I'm at the final version of inference Rmnn. So all the parameters are plugged in. This is the full version of the complete code. Okay, so I hope everyone had an opportunity to play with Jupyter Notebook before. If not, I will get you through this. So let's first open the inference Rmnn notebook. Inference _ Rmnn IPYNB. Yeah, it's quite a bit challenging because we were not able to see your screen. In case that you run into any questions, please just feel free to ask. So to run the Jupyter Notebook is actually fairly easy. This Jupyter Notebook is composed of different code blocks. So click in the first code block and click this Run button. So the first code block import different dependency libraries and print out the current PyRmnn version we're using. There's some warning messages. You can feel free to ignore it. Oh, I guess I clicked it twice. But eventually you should be able to see PyRmnn version got printed out here. We're using the version from this February, 2020 February. Cool. So moving down to the load image file and the define model part. So we're going to run image classification based on 3 classes. Class 0 means the image is normal. Class 1 means we detect pneumonia in the X-ray image. Class 2 belongs to the COVID-19 category. So as mentioned, we were able to utilize DarwinAI's open source model, COVIDNet CXR4-A model to generate this Tensorflow Lite file. Since this file is located in the same directory here, this COVIDNet file, so we can simply plug in the model file as COVID-19.tensorflow Lite. So moving down, we have to plug in some of the parameters. You can pick and choose which image file under the assets folder you want to use for diagnose purpose today. So I think by default, I'm going to use ex covid.jpg. It's one of the files under this assets folder. So once you are done, click the Run button. So now we load the image file and the model. In the meantime, we run through the pre-processing stage to make sure our image is inference ready. So one thing I want to mention here, it's in the README file. So if you want to understand the structure of this COVIDNet TensorFlow Lite model, you can use one of the tools like TensorBoard or Netron. So this is what the model looks like. So the link to this tool is in the README file. You can simply click it. I think you can simply click on the link and open the TensorFlow Lite model. But anyway, this is what the model looks like. Let me zoom in a little bit. So if you click on this, you can see the input layer information. So for our input layer, its name is input_1. It's of float number 32. And this is the dimension of the model. I should say this is the dimension of the layer. So for the output layer of our model, the layer name is norm_dense_1 is a softmax model. It's also of float 32 format, and this is its dimension, 2-dimensional. Cool, yeah, this type of tools will be very handy for your debugging purpose. And we will be able to see some of this information in our code shortly. So go back to our Jupyter notebook. So far, you should have completed the load image file and the define model process. Now let's move on the most critical part. Let's create a parser for our Tensorflow Lite model and load the network. So you can refer to the README file, copy and paste, or you can simply refer to the inference arm final underscore final file, just a copy paste from here. So since we're using a TensorFlow Lite model, we have to first create an Rmnn parser for TensorFlow Lite. Rmnn also provide parsers for TensorFlow, Unix, and Caffe. So it depends on what model you're using. You have to pick and choose which parser you're going to use. So simply copy this. Go back to our inference underscore Rmnn code, paste it here. And we're going to do the same thing to the load network file. So right now we already defined the model file as covetnet.tensorflow Lite. Once we created our parser, we have to use a parser to create the network from the model file. So copy this line and again, plug it back to our code. Once you are done, simply click the Run button. So now parser is created and we load our network to Rmnn. As the next step, we have to retrieve the input binding information from our model. So this part of is fairly straightforward. Even if you switch to another model or another parser, you don't have to change this part of the code. So simply click Run, and you should be able to see output information like this. Input name, this refers to the name of the input layer, exactly the same as what we observed from our virtualization tool just now. So input name should be input_1, and this is the input tensor information. If you remember, we're talking about, if we go back here to see the virtualization of our model, so the input layer has a name of input_1. It's of float 32 format, and it's 4-dimensional. So this is totally aligned with the output here. Okay, once you're done with this step, next step, we have to create a runtime object, which will eventually to run the inference. So simply move your cursor here and click the Run button. There's no direct output from this code block. So now we're going to define our backends. So like what Kyle introduced in the presentation, Rmnn now supports CPU, GPU, and NPU backends. In our case, because our instance is running on the Graviton instance, we only have CPU backends. But if you run this on a device like High Keyboard or RockPi, Odroid, all these devices actually support Mali GPU. So you have to include GPU backend as your preferred backends. So again, we can copy and paste our preferred backends to this line. Move down a little bit. So I included the GPU acceleration here, but frankly, in our case, you will not be able to observe any difference. CPU reference, this is the software reference kernel. So in case CPU hardware will not be able to provide acceleration for our operator, we can revert it back for the software implementation. So copy and paste your preferred backends here. Then don't forget to click the Run button. So now your preferred backends has been picked up by Rmnn. As the next step, we're going to run the whole graph through Rmnn for optimization. This is actually where the magic happens. So in this optimized code, Rmnn will pass through each layer in your network, trying to figure out what's the longest path for a part of this network to run on a single backend. Is it CPU, or is it GPU, or is it NPU? And Rmnn, in the meantime, will try to optimize a specific part of your model for the hardware you defined in your preferred backends. This is especially true in the NPU case. We have actually a lookup table. In certain cases, we're going to replace certain layers in your model and optimize it specifically for the hardware. So now, after you optimize the model, the optimized model is saved in this parameter, opt_network. So after this part, you have to load the optimized network into your Rmnn runtime. So just plug in opt_network here. So this part, just to make sure you're using the optimized network instead of the original version. So once you're done, click Run button. Yeah, the following part should be straightforward. We're going to pass the output binding information and make output tensor. Just click through this part and you should be able to see output like this. Again, this is the name of the output layer. It's two-dimensional, which are totally aligned with what we observed here. So this is the name of the output layer. This is its dimension. Okay. Yeah, I hope everybody is able to moving along. So if you have any questions, feel free to ask, please do not hesitate. Yeah, so we're going to revisit the profiling part in a little bit, but right now you can just click through. Now, this is the part where the real inference takes place. There are a couple of parameters you have to plug in. So in-queue workload is the line that we trigger the image inference. So you can copy and paste the parameters of this one to your code. Only 3 parameters. The first parameter is the graph ID, then followed by the input tensors we created and the output tensors. Okay, click through. This is what you should be able to see. So this is the image we put into the assets folder. And here you can see the inference time and the predicted result. So with Rmnn, we were able to run the inference in roughly 220 milliseconds. So out of 3 categories, normal, pneumonia, and COVID-19, these are the percentage of the predicted value. So because the COVID-19 has the highest possibility, our prediction is this patient unfortunately caught COVID-19. So that's basically it. So this is, I think we really don't have many lines of code. And with this, you are able to use Rmnn for image classification. And frankly, if you want to extend this to different models, different images, the only part you have to change is probably this part. Depends on your model format. You define the corresponding parsers for that, and you import your binary file. The other part of the code should be just plug and play. You don't have to make any changes. Cool, now we're going to compare the performance results between Rmnn and Tensorflow Lite. So move down a little bit. After the view profiling result part, you will be able to see this code block, Rmnn versus Tensorflow Lite performance benchmarking. So this part, we're going to use Tensorflow Lite as the inference engine to run the same image inference. So you don't have to do anything with the code, it's complete. So basically just click through these code blocks and you will be able to see the inference result with Tensorflow Lite. See, in my case, it actually took over 600 milliseconds to finish the same inference. Yeah, prediction result is identical with Rmnn, but the time it takes is almost 3 times of what Rmnn requires. So if we go back here, you can see this one is only 220 milliseconds versus TensorFlow Lite takes roughly 630. I hope we're giving you an intuitive understanding of the performance enhancement Rmnn will be able to offer. And now I will just give a few minutes to you to play with it. And also at the bottom of our README file on the last page, you can see there are 2 hands-on exercises. So if you're able to finish what we just walked through, feel free to tweak some of the parameters, plug in a different image from the assets folder and check the inference result. Access to is about using Rmnn profiling APIs to benchmark per layer performance. This part of the code is included here already. All you need to do is to uncomment 2 code blocks. One is the enable profiling code block. Just remove the pound sign in front of each line to uncomment it. And do the same thing with the view profiling results part. Just uncomment these lines. And here you will be able to see, for each layer in your model, where does it run? Is it using CPU acceleration, or if it's using GPU, or simply the software reference code, and the time it takes for inference. Yeah, this part of profiling information will be extremely beneficial when you design your machine learning model. Yeah, feel free to play with it. If you have any questions, just let us know. I hope everybody was able to get some inference results with your Jupyter notebook.
Wait, we do have a question. Is there any way to check out the optimization details between CPU, GPU, etc. with Rmnn?
Yes. Yeah, it actually belongs to some of the advanced topic I don't think we will be able to cover today. So in our CP, actually, let me refresh my memory a little bit. In Rmnn, we do have a tool called, actually this belongs to part of, we have a separate SDK called ARM Compute Library. And there are a couple of tools provided as that part of SDK, which is called CL Tuner. This tool is specifically designed for GPU tuning. And through Rmnn, we exposed some of those APIs. So by utilizing this tool, you will be able to understand the performance on the GPU and further fine-tune your model to best fit into the different hardware backend. We will have some documentation on that be published by next month. Sorry, I don't have more information at this point, but please go back to our developer portal and you will be able to find more information there. Yeah, thank you, Kyle. Yeah. So Kyle posted the link of ARM Compute Library to the chat window.
Are there any other questions, or is anyone running into any issues running these notebooks? You can also feel free to unmute too. There's only So many of you.
The same code will run out of the box seamlessly on device like a Raspberry Pi. So if you happen to have a Raspberry Pi at home, feel free to test it out later today. Thank you.
With that, any questions for either Wei or Alex? I know there's a question from earlier for Alex from Sai. Are medical professionals involved in the design audit process to weed out false positive negatives for the COVID net work you do?
Great question. The answer is yes. So we're working with actually a number of different clinical institutes as well as clinicians from around the world to not only identify these kind of potential, I guess, gaps or issues through model auditing, but we've also had cases where the model auditing actually gave additional insights in terms of things that they otherwise wouldn't have thought about. So if they were looking and say, oh, wow, it was able to identify something that I didn't think was a particularly useful cue for COVID-19, but in hindsight, looking at this, as well as what the models picked up, they actually found it to be quite useful. And so in addition to that, we've also worked with clinicians on not only just validation of the networks themselves from an auditing perspective, but we've also ran through a lot of types of tests to see if we're actually conveying the right information to them.
Great, thank you, Alex. Yeah, did that answer your question, Sai? Perfect, perfect. Let's see. What is being used as ground truth to determine positives? PCR? I don't know what that is.
Yes, so positive PCR test is one. So in many of the cases, they're not only received positive PCR test results, but they've also been clinically confirmed.
That was a question I had from one of the attendees, Paul, which was, I get an error saying COVID-19 TF Lite is not UTF-8 when I tried to double click the file. What's the correct way to open it?
Yeah, so for opening like TensorFlow Lite files, you're going to want to use the interpreter built into TensorFlow. That'll just give you the layout, or something like TensorBoard. If you double click it, it's just going to be, it's a protobuf file, so it's not going to work. Right way, you would say.
Yeah.
That.
Yeah, and or this one, it's my personal favorite because it's lightweight, it's easy. Nitron.
Yeah, this one is nice. One.
Yeah.
What's this one's called again, Wei?
Nitron, this one. So if you Google Nitron, you will be able to find the link. Actually, I included the link in the README file.
That's going to be the best way to interpret those TensorFlow Lite files. If you just open it yourself, it's just going to be, it's just code. It's just a protobuf.
Yeah, so this is what our TensorFlow Lite model looks like. It's a fairly complicated model.
Well, that's what happens when you let a machine design it to be optimal. But I just want to add that Netrun is actually a wonderful tool to use. It's also available both in this form as well as in binary form. So I've used it under different situations.
Cool. I did not know that. Let's see. Another question from Chuck. How do you deal with timing differences between time image is required versus when other tests are performed when validating positives?
So very good question. So in general, the time span associated with them are actually quite short in terms of all the tests being done within pretty much hours of each other. There's always going to be a bit of a disparity, but because of the time frame for all the tests are usually done all in one shot, one after the other, associating them with as a single instance is actually quite reasonable, and it's regularly done. But to add a bit to that, we've also have data cases where a patient might go back for multiple acquisitions, in which case each individual acquisition is timestamped.
That was a good question. Any other questions regarding Rmnn, Pyrmnn, the COVID-net, Darwin AI, everything that's going on there? Do those multiple acquisition impact the current or future models? That was another question from Chuck.
So it impacts both current as well as future models. So in terms of current models, we make sure that they're actually trained because with multiple acquisitions, it allows us to analyze the disease at different stages, because the appearance of disease of the same disease could change over time based on progression. So this is useful in two cases. One is it allows us to see a much better diversity from a detection perspective. The other thing that's also important is because we do also have networks for risk stratification as well as severity detection. So having it at different stages of severity also gives the network more diversity to learn from, to better judge not only if somebody has COVID-19 or not, but also the severity and what stage they're at. So that's one particular use of it. But of course, we also make the very clear distinction to associate multiple acquisitions for the same patient together to avoid any kind of data leakage.
Let's see. Sydney asked, share the link for the COVID-net TF Lite file. You can download it directly from the COVID-net folder in the Jupyter Hub if you'd like. It's also documented online somewhere, right? Wei and Alex?
It will be published by next month. It's in the queue right now.
Got it. Yeah. So we'll have this guide up later, but for now you can just download it directly from this Jupyter Hub. You can right click on the COVID-19 TF-LET file and download it with the PDF, and all the code would probably help as well. Are there any other questions from anybody?
Happy to answer any questions, even if it doesn't relate directly to COVID-net, just on, I guess, model creation, design, generation in general.
Okay, let's see. A few questions from Wawa. How long does it take to develop such models? How do you decide if the model is ready to use in real cases?
A very good question. So in general, using this human machine collaborative design approach, we're usually able to design models on our order of days and weeks. In terms of how long it takes, it really depends on the actual complexity of the types of models that you have. So for example, for situations more, for example, in machine perception or NLP, it usually takes a little bit longer. If it's for situations that are beyond classification, such as, let's say, object detection, segmentation, so on and so forth. So, but in general, by taking this automated approach, which is guided by human design requirements, it actually greatly accelerates the process. So how do we decide if a model is ready to use in real world cases? That's a very good question. And for us, it largely depends on the actual model auditing process. And so with the model auditing process, what I've covered is largely on whether or not the model is actually performing as it should. So making the right decisions for the right reason. So that's a very important criteria. What we also surface as part of the auditing, which I did not cover as much about, is in terms of performance bottlenecks of different designs. So we know it's ready not only is when it's making the right decision for the right reason, and we've ironed out those dependability issues, but it also is ready when we find that the performance trade-offs for operational requirements are met in the way that we want. So one example is at the start of the development process, we might say, okay, these are our current requirements. We need it to run on an ARM processor as, you know, at this FPS, and it needs to achieve these particular metrics. But when we create using GenSynth, what we often find are networks that meet these requirements, but they have different trade-offs, and it allows us to figure out what is appropriate for, let's say, a cloud ARM deployment or a edge ARM deployment. So we had many situations where the requirements were, I guess the way we set up, they were too relaxed. So there were situations where we wanted 90% accuracy, but all the models generated exceeded 92, 93% accuracy. So then at that point, we can then find a trade-off. Okay, great. This one achieves 93% accuracy, which isn't the top one, but it is orders of magnitude faster than the other designs. So by taking these performance trade-offs into account, as well as understanding whether or the model is actually giving replies in a trustworthy and dependable way, that's when we know it's ready to deploy in a real world case.
Cool. That was was that a good answer, Wawa? There is another question from Will. How have you been able to handle data gathering and training given HIPAA rules?
Yes, so
I guess that's HIPAA.
Yep, that's HIPAA. So HIPAA is one thing. So given HIPAA, as well as the key thing is that because we're doing things in the healthcare field, ethics becomes very important. So getting REB approvals, so on and so forth. How have we been able to handle it? We've been able to handle it in a slow but methodical manner, because what we want to do is whatever we do, we need to make sure that it meets ethical standards as well as dependability standards. So the answer is it's slow, but we're doing it in the right way.
That's great. That's great. Any other questions from anybody else? If that's it, Wei, Alex, do you have any closing statements you want to make? And also definitely thanks to both of you. This was very good. I enjoyed it.
Wei, would you like to go first, or would you like me to go?
You can go first. Sorry.
Okay, no problem. So I just want to thank everyone for listening. And the other key thing is, because again, the COVID-19 initiative is fully open source, open access. I implore you to actually take full advantage of it, customize it, use it for your own needs, play around with it. But the other key thing is that we're always looking for contributors to help with the cause, because the more people working on it, the more different perspectives we get, the more improved models we're able to achieve. So hopefully we could all work together to help, I guess, fight the pandemic we have at hand, because it's not going away. So we need to be proactive in trying to help with the management of the pandemic and the disease.
Yeah, the only thing I want to see is we only have 1.5 hours today. I hope you get a taste of what Rmnn looks like. As Carl mentioned in his presentation, Rmnn is not only being utilized in IoT space, we have been contributing upstream to Android APIs as well. So if you are an Android developer and you use Android APIs for development, you are actually already enjoy the performance enhancement Rmnn provides. So Rmnn not only can do image classification, we're rolling out sample applications for object detection, super resolution, speech recognition. By end of next month, you will be able to see Debian package release for Rmnn as well. So go to our developer portal, machine learning part, and you will be able to find more Rmnn resource there. Thank you.
So based on that, I'm definitely looking forward to a mobile version of CovetNet platform, as well as I'm also actually very much looking forward to apply many of our highly efficient neural network architectures using Rmnn.
That's great.
All right, with that, I would say thank you, Alex. Thank you, Wei, and thank you everyone for attending. I will leave the Jupyter Hub up for the next 20 minutes or so, so feel free to download the files if you want, just for the time being until we release the document that's going to be out later to go along with them. And I hope you have a great rest of your DevSummit.
Thank you for everybody's participation. Thank you, Carl.
And one last thing, I hope everyone stays safe in these trying times.
Cool. Thank you. Thank you all.